Welcome back to Unit 3 of our course, and this is Lecture 3. Now, what we did in the last lecture was to introduce this new boundary condition that for the electrochemical potential that we could use to solve the diffusion equation and get the correct answers, ones that actually includes the ballistic resistance. And as we showed, that this new boundary condition kind of amounts to having these extra resistances at the interface. Now, what we want to do next is try to show where this boundary condition comes from, except that we need to do that in 2 steps. And we'll take the first step in this lecture. That is, in this lecture, what we'll do is we'll introduce this concept of quasi-Fermi levels. The idea that there are 2 quasi-Fermi levels, one for right-moving carriers and one for left-moving carriers. And we'll show that the correct boundary conditions for these quasi-Fermi levels is that the mu plus, the one for right-moving carriers at z equals 0 is mu 1. That is, this mu plus has to connect up to mu 1 here. Whereas when you look at mu minus, it has to connect up to mu 2 at this end. And what we usually call mu, what we have been calling the electrochemical potential, is actually the average of the 2. So what we derived in the last lecture was the appropriate boundary condition for this average. And what we'll do in this lecture is we'll try to obtain the correct boundary conditions for these 2 quasi-Fermi levels. And then in the coming lecture, we'll connect it up. We'll show that this implies this. How to get from here to here. That's what we'll do in the next lecture and thereby complete the story. But right now then, what we're trying to do is explain what's this mu plus and mu minus and why these are the appropriate boundary conditions to use. Now, for this purpose, it's useful to start from the ballistic end. That is, this is the picture, of course, for any channel, which could be very few, could be very short or could be many mean free paths long. But let's take the case of the ballistic limit, which means where the length of the channel is much less than a mean free path. In that case, you see this middle region, this channel resistance, that's a very small quantity because L is much less than lambda. And so the entire resistance is just the interface resistance. So in that case, what you'd expect is that the way the electrochemical potential will vary is inside the channel, it will hardly change. Why? Because that resistance is small. This change in potential kind of corresponds to the resistance. So what you expect is this will be flat inside. And the question is, why is it halfway in between? Now, what we like to argue is that actually there are these 2 separate quasi-Fermi levels. And if you looked at the quasi-Fermi level for right-moving electrons, it would be up here, connecting up with mu 1. And if you looked at the quasi-Fermi level for left-moving electrons, it would be down here, lining up with mu 2. The question is, why is that? Now, to understand this, let's think a little bit about what this electrochemical potential represents. As you know, it comes from the Fermi function. The Fermi function has this property that if you go to energies high above mu, it's 0. If you go to energies way below mu, it's 1. Right? So any state below mu, way below mu is completely filled. It's 100% chance of being filled. Fermi function is 1. Up here, 100% chance it's empty. Fermi function is 0. And at low temperatures, this transition is actually quite abrupt. That is, the energy range over which this change takes place, that's on the order of a few kT. So when temperature is small, you have what's called a brick wall type of thing, where it goes abruptly from 1 to 0. And so when you're thinking about things, it's often easier to think in the 0 temperature limit, because that's still approximately correct even when the temperature isn't really 0. So when I draw an electrochemical potential up here, what I really mean is that all the states below it are completely filled in this contact. Similarly, when I draw the electrochemical potential in this contact here, it means that all the states below it are completely filled down there, you see. But here, the states are empty. So if we consider this energy range here between mu1 and mu2, then if you looked at the Fermi function, it would be 1 in this contact and 0 in this contact. 1 here because it's below mu, 0 because it's above mu. So here then we have a situation where in this energy range, there's lots of electrons filling up these states, whereas these states are just completely empty. And what we'd like to argue is that as a result, all the right moving states would be completely filled and all the left moving states would be completely empty. Now for this, I've often used an analogy that expresses the situation quite well. It's like, think of two cities, and I use a local example in the sense, you see, I live in this small city called Lafayette, and it's to the south of Chicago. Okay. And then there's a highway in between, and as with any highway, there's the northbound lanes, and then there are the southbound lanes. So now think of a situation where something big's happening in Chicago. So lots of cars at the Lafayette end are trying to get on the highway. They all want to go to Chicago. And not surprisingly, there's no one trying to come back. So at the Chicago end, it's all kind of empty. That kind of illustrates the situation here. F1 equals 1, F2 equals 0. So what would you expect if you looked at the occupation of the lanes on the highway, which is like the occupation of the states in the channel? What would you expect? Well, what you'd expect is that all the northbound lanes would be completely filled and all the southbound lanes would be completely empty, right? And that's exactly what would happen here too. All the right moving states, that's kind of like the northbound lanes, they're all completely filled up to here. That's mu plus. And all these states are completely empty. That's the mu minus. So this is the situation when you have ballistic transport. That is, length is much less than a mean free path. In this context, what it means is that when a car gets on the highway, it has no way of turning around. It's ballistic, so it has to keep going straight till it gets out at the other end. Whereas in practice, if you had the diffusive conductor, you see that would correspond to a situation where cars could turn around and come back. So in that case, what you would expect is, you see, on the northbound lanes, you start out with bumper-to-bumper traffic, but then as you go along, it kind of thins out. Why? Because some cars turn around and go back. Similarly, when you look at the southbound lanes, it all starts out being empty, but then it gradually builds up. Builds up because cars from here have actually turned around. So again, in terms of these quasi-Fermi levels, what you expect is something like this, that the quasi-Fermi level for right-hand electrons starts out at mu1, but as you go through the channel, it gradually goes down. And if you look at the quasi-Fermi level for left-moving electrons, it again starts out down here, but then gradually builds up. So the boundary condition then that you expect for this electrochemical potential or this quasi-Fermi levels, this mu plus and mu minus, is that mu plus at this end should be equal to mu1. In other words, if states are filled here, they will want to be filled inside as well. And if states are empty here, it would also want to be empty right there. See? Now, the key point here, of course, is that when you think of mu, then think of it as something that tells you the degree of filling of the states, not as something that signifies the average energy of the electrons. Because, you see, if the average energy were actually going down, then there must be some dissipation. And as I've mentioned before, on this scale of things, dissipation usually happens somewhere else, mostly in the contacts. So when I draw this mu going down like this, I don't imply that energy is being dissipated down here necessarily at all. All that it says is that the number of electrons, density of electrons will keep going down. And that we expect just from common sense. I mean, just based on what I said. If you had a highway with lots of cars trying to get from south to north, the northbound lanes would be completely filled. And then if cars got fed up and started turning around, then what would happen is the filling would gradually go down and the other side would go up. So the basic boundary condition then we expect for these two quasi-Fermi levels. So the first point is that you expect there to be two quasi-Fermi levels. Two levels that describe the occupation of the northbound lanes and the southbound lanes. They don't have the same electrochemical potential. And the second is that the boundary condition on these quasi-Fermi levels is mu plus at z equals 0 is mu 1, mu minus at z equals L is mu 2. So with that then, we are ready to move on to the next step, which is, these are the quasi-Fermi level boundary conditions. Question is, how do we connect it to the boundary conditions we talked about in the last lecture, which is for the average of them, that is this electrochemical potential. So what we'll show then in the next lecture is how what we just obtained implies what we had deduced earlier. Thank you.